My name is Venkat Guruswamy. I'm a senior scientist here at the Simons Institute, and it's my pleasure to invite you to one of the highlights of the Simons Institute activities, which is the Meet the Fellows program of talks and introductions for 2 days, which happens at the beginning of both the fall and spring semester. As you might know from meeting other fellows, we have an amazingly large and diverse collection of fellows semester after semester. That is in fact one of the big highlights of the Simons Institute, and it perhaps is really the singularly unique place with such a concentration of postdocs focused on theoretical computer science related topics worldwide. And of course the fellows are crucial for a lot of the activities which happen in the programs and all the things we get to brag about as products of the program. So we kind of celebrate that in the beginning, and to get to know the fellows with this event, which is sequence of lightning talks by all the new fellows and any existing fellows who are interested to share updates. And so that's what we're going to be doing today and tomorrow. So we have a busy schedule of amazing talks, and so we'll begin it now. So just one request: as you see, the schedule is quite packed with 15-minute slots, and the anticipation is that you would do a 10-minute talk, and then I will kind of indicate to you, and that gives us 5 minutes for Q&A, transitions and so on. So please try to adhere to that, and that will really help. And if you want to chat more, I'm sure there is plenty of break time and other things. You'll all be here this semester, so there'll be chances to discuss in greater depth. With that, let me introduce the first session. We're going to have 4 fellow talks from the Graph Limits and Processes on Networks program. And the first talk is by Claire Donnat on understanding the geometry of graph neural networks.
All right, thank you very much. So yeah, my name is Donnat, and I'm currently at the University of Chicago in the statistics department. And so I'm going to talk about some of the work we're doing with several students on understanding the geometry of graph neural networks. So perhaps to start off with a little bit of introduction, in the types of problems that we're considering, where you can actually pretty much understand them as a data integration problem. So what you observe is a graph on n nodes, and that is typically encoded through a binary adjacency matrix. And on top of that, you also have node features. So let's say they're p-dimensional. And in these types of problems, what you're interested in is actually predicting a signal of interest. So whether it's node prediction or edge prediction. So perhaps as a little bit of an insightful example, so the graph I show here is from a paper by Zitnik, Argol, and Leskovec in 2018, and that tries to use graph neural networks to model side effects of interactions between drugs. And so in that case, the adjacency matrix actually allows you to model interactions between drugs or proteins. So you have protein binding activities and drug interactions, so different types of nodes, different types of node features, and different types of edges. And what you're trying to do in particular is, for instance, predict drug-drug interactions. So what has been the recent trend in machine learning is to actually use graph neural networks for this kind of problem. So graph neural networks are basically an adaptation of the deep neural network machinery to the graph setting. And it relies on 2 essential ingredients. The first one is a spatial convolution, which you can understand as a generalization of what GNNs do to the graph setting. And the idea here is to say, well, okay, so I want to integrate adjacency and node features. How am I going to do that? So for each node, I'm going to integrate, make a new representation of that node that has its own features plus that of the neighborhood. And I do that by doing just a simple, you could compare it to message passing. So just a simple weighted sum of that node's features with its neighbors. And the sum, the weights are determined by the choice of the convolution operator, the spatial convolution operator, which typically in the GCN setting is just the augmented adjacency, which is symmetrized by dividing by the degree matrix. Then, of course, you do like linearity plus bias, non-linearity, like the neural network, but that's, just quite simple. And then the second ingredient is actually the reconstruction objective, because you change these models end to end. Okay, so the problems with this has had good success across problems, etc. But there's still some issues which make GNNs perhaps interesting to study. The first, you could say mainly there are 3 main issues with these type of techniques. First of all, the properties are never very well characterized. Like, how do they actually extract patterns and are able to extrapolate? For instance, in this particular example, is it the case that some spatial convolutions are better suited to the study of homophilic networks or interaction networks like this one? You also have evidence that GNNs are sensitive to perturbations, like for instance, edge deletion or additions. And in a setting like this one, for instance, where you don't expect all drugs to be well studied or characterized, you actually do expect a lot of edges to be missing, at least for now. So this is also problematic. And finally, of course, GNNs are not very interpretable, nor are they endowed with any measure of uncertainty. So this makes it very hard to deploy in any sort of practical decision-making setting. So perhaps as a way of trying to understand a little bit more what GNNs are doing, it's good to go and look at what people in the statistics and applied mathematics literature are doing. And in particular, we have a rich literature on network models, and so parametric, non-parametric, etc. And perhaps the one that sort of is the most similar to what GNNs are doing are latent space models, as proposed by, for instance, Hoff. And so in that case, the idea is that, well, you have an underlying manifold M, and what happens is to create the data that you're actually observing, what you need is some sort of sampling mechanism over that manifold. So let's say it's pi, and based on these sampled points on the manifold, you can actually generate the feature data and edges, right? So, and for instance, the function G here could rely, for instance, on the dot product between the two latent representations or their distance, etc., depending on the type of data. And so GNNs are actually, can be compared to one of such latent space models, because what they're trying to do to some extent is estimate this Z here. And the way they do that is a little bit akin to what variable encoder does, right? So they try to mix in a way the adjacency and the feature matrix to get a representation of this matrix Z. So with this in mind, basically, what we could try to consider is to say, well, actually, okay, so to try to understand perhaps a little bit what GNNs are doing, the bias that they carry, their robustness, etc. Maybe it could be interesting to try and see, well, actually, if they're trying to recover this manifold, like how are they doing? How are they doing at the job? Are they also able to disentangle the manifold from the actual sampling density? So today I'm just going to talk about some preliminary work that we've done on the topic, and we actually focus on just the convolution operator. And the idea here is to say, okay, well, one of the crucial ingredients in this type of setting is this convolution. And so we distinguish two families of operators here, the symmetric versus the row-normalized one. And the symmetric basically is just saying, okay, well, we're going to take the adjacency matrix like GNNs, right? We're going to add self loops, except I have a weight beta here, right? That allows me to sort of almost interpolate between like GCNs and just the simple MLP setting. So if beta is very large, you could think that's the node's feature, the source node is dominating. And then we're going to divide by the degree matrix, but at the power alpha, where alpha varies between 0 and 1. So you have this kind of symmetric operations, and then you have the row-normalized one, where basically you take the random walk version of this. And where this gets interesting is that, well, the reasons why we did this was that we are interested in the resemblance between operators, between the operators that the GNN convolution use, right? So assume you had a model with no node features, so you just replace X by the adjacency, and you do sort of discrete convolution like this, right? You stack them up, so you have S K times identity, and diffusion map. So something that has been introduced in the early 2000s by Kaufman and Lafont. So the two authors here proposed spectral embeddings of this form here. So basically, they take a bit like us, the degree at the power alpha times their similarity matrix between objects. They divide by the degree, and they take a continuous sort of power of this to actually recover the underlying manifold. Where this gets interesting is that Kaufman and Lafont actually comes from the applied mathematics community, and they have very interesting discussions about the potential of this type of spectral embeddings to actually recover the underlying Laplace-Beltrami operator. They show that this embedding typically is non-biased if the sampling distribution on the manifold is uniform, and they actually discuss the case of non-uniform sampling cases. So something that is, so they have a nice theoretically grounded framework and a discussion on effects that don't really exist in the GNN community. So the first thing we did was say, okay, well, they have actually a discussion on like the importance of choosing this alpha and the relationship it has in sampling density and etc. So let's try it out. So let's try and vary, for instance, the alpha. So this is just experiments on a synthetic, on Cora, so a well-established benchmark in the GNN communities. And here, so like the legends is a bit, I changed the names, but the red is basically the symmetric one, and the blue is the like random walk version of it. And you can see that there's an interesting change of phase at sort of alpha equals 0.5, where the performance starts to drop. And this effect is actually observed with different magnitudes and I guess amplitudes across different data sets, right? Where it seems that there's a local optimal at 0.5 sometimes, and then it dips. Actually, here it starts. Yeah, I guess the optimum is a bit later. For I guess so the random walk version, so the blue one, the effects is a bit different. So this just goes to show that choosing alpha is actually important and must intervene somehow in the geometry of the manifold that is being recovered. So we basically, in what we did, so we have very simple ways of trying to understand actually like the geometric organization of the embeddings, sort of in the trying to characterize exactly, for instance, where it is compared to like, so this is in a way the bias term, so it's where it's anchored, and the the H is in a way the like, how much it varies around this bias term. And you can actually show through simple derivation that when alpha is less than 0.5, this bound is an increasing function of the degree, which means that high degree nodes are going to be able to spread much more. And that effect is actually reversed as alpha increases. And this is a synthetic experiment where you see alpha equals 0.2 here and alpha equals 0.7 here. And the blue the blue nodes here are the high degree nodes. And you can see this sort of reversal of, they're on the outskirts in a way of the data. This is the latent component. And whereas at the center as alpha increases. This effect is not so much present, is at least hindered when you're considering row-normalized convolutions. And so this is interesting because it goes to show that in a way your assumption, for the row-normalized, the symmetric convolutions, it goes to show that alpha is actually important, controls how much variability your high degree nodes have, and thus potentially what kind of influence they must have. So for instance, here as a function of alpha, we have two settings. One, the blue one is the node decreases with the degree, whereas the noise increases with the degree when for the brown one. And you can see that as expected to some extent for settings where the low degree nodes are more trustworthy, the performance is actually higher when alpha is equal 0. So they have potentially more influence. So yeah, so basically we do the same, like this effect is actually a little bit hindered for row-normalized operators. And yeah, I mean, we have several plots. Essentially, let me conclude here because my 10 minutes are over. So this just, this is currently just like partial conclusion on what we've begun to do on trying to understand how the different components of the GNN sort of machinery relates to properties and recovering, the underlying manifold. Here it just goes to show that the right choice of there is such a thing as a right choice of convolution operators. It actually has is very much linked with what prior you have on the degree. Like, is the degree an essential feature of the data set, or is it due to, for instance, sampling density? And are there ways to mitigate in a way the effects of this? And thank you very much for your attention. And if you have any questions, I'd be happy to take them.
Okay, so the way we'll do is we'll take questions while the next speaker sets up. So to keep going. Any questions? We have time for a quick question or two.
So is it just the degree that's important for the choice of author, or is it just also like the local structures maybe? Like...
Look at the degree. It's a thing that we could look at currently, right? I guess we try to look as well, like the curvature as well, like just empirically if it has to do. That's something we're trying to understand as well. Like, is it, like the degree is the simplest in a way setting, but it seems to be highly correlated so far. So.
Thank you for the talk. I'm wondering, you mentioned the use of diffusion maps, and my understanding is that in general you use it when the manifold is non-linear. Is that something that you're looking at to characterize like different non-linearities in the manifold described by the data? I'm curious about details on that.
Yeah, pretty much what we're trying to do is try to understand. So there's the way GNNs operates is very reminiscent of the diffusion maps, and there's like this nice theoretical framework, and they are a nonlinear sort of embedding method, right? They allow, and they actually show that you can recover the Laplace-Beltrami operator, and so the GNNs do that, but on top of that, they have this added difficulty that they're actually using node features on top of that, right? So, but still, if you again take X to be just the identity, you sort of put back into the diffusion map setting, and so yeah, basically what we're trying to understand is how GNNs sort of, in a way, are an approximation of the diffusion map, or do they actually converge to the same thing from different angles? And is there anything we can actually learn from the diffusion map setting that also transfers to GNN settings? So for instance, all their work on saying, well, what, for instance, when you can't assume that the sampling distribution is uniform, like what does it mean for the recovery of the locations of the manifold, et cetera, et cetera. So
Thank you.
Right. Thanks for the great talk. And let's continue. The next talk is by Shuang Go and on transmission neural networks.